Okay, so good afternoon, everyone. Can everyone hear me? I hope so. Okay, so welcome to the last session of this e-learning course. I'm the chair of this session, and today we have the great pleasure that the Director of the Diagnosis and Interventional Adaptive Imaging Lab, Professor Felblinger, is here with us and will talk about the MR hardware and safety aspects. So thank you, Professor Felblinger, for accepting the invitation. And without further ado, the stage is yours.
Thank you, Celine. Okay, so we can start, and we will talk about MR safety, but MR hardware at first. And just my topic is to go through this hardware basic stuff, but again, it's a basic course. We can have more information about this. But my idea is just to speak about limits on hardware and some characteristic that you should know if you do MRI. I will just start a bit about safety for patient safety and also some worker safety just at the end. As you know, there is another course called Advanced course for lecture of MRI, and there I will speak only about safety, but more advanced safety issues. So just some slides to come that you can come on the course and start to listen. This is the basic stuff. You have to do an MRI. You have to do true and sequence. You know that you have to do a slide selection, and after you have to fill the cast space, and after you have the image with a Fourier transform. And this is, I think you know this now. And what we have here, we need a sequence where we combine RF, phase encoding, frequency encoding, and do our acquisition. I think this is the basic stuff. But what my goal is today, just to go behind this console. Console, you have the sequence and you have the DICOM image at the end. But to do all this, we need a sequencer. We need a lot of power. I will go through this. Of course, a magnetic field, gradient of magnetic field, radio frequency coil. And after you go back here with the signal and you have all the data in the cast space and you can have your images. So the goal is to go through this and just a small video again. The patient is in the middle of patient of B0. After you send some radio waves, this is going inside the patient. That's how you go to get some RF back from the patient. What we need, this is the basic stuff again. You have the resonant frequency here, and you have this MRI for proton, phosphor, or carbon. So I will go through the magnetic field B0, some information about electromagnetic wave, what we will call B1, the gradient, and just some information about the pulse and so. So the first part of the system is the magnetic field. This, you have seen this probably, but what you have to see that the patient is in the middle of the system. He is in the middle of the solenoid. Basically, it's a solenoid. You will see a bit just later if you go in advanced course. You have several solenoid. Here this is an example here of the body of the B0 of the MRI, and you will see that there is another coil here. But basically, what is the focus today? Just to push B0 the highest as possible, so we have the highest SNR. But today in clinical application, we have generally 1.5T or 3T, and this is enough for a lot of cases. Of course, we have some people working at 7 Tesla or even higher, 11.5, and there's a competition to go higher and higher. But you see the difference here. This is an example for the French system. It's not my lab, but the C in the middle is the patient. The B0 to do 11.7 or 0.5 Tesla is huge. Okay, this is only for research, and for clinical stuff, you have only this type of machines here, even for CNT. The first information, what we have here, we need a lot of current to have this 1.5 T or 3T. Generally, you need 500 ampere or even more. And the first point is to say that all the coil here is placed in a supraconductive material. What does this mean? You put everything in a liquid helium, minus 269 degree. This means that the resistance here goes to 0 ohm. And this is very funny for MRI. If you start the current in the coil, this continue to flow without resistance and without outside power supply. If you have not a superconductor material, you will need a lot of power, 500 ampere, and so this is a lot of power. And for example, for 1.5 T, I just roughly calculate this will need 30 kilowatts just around the patient, and this is so many energy that you cannot cool it. So the first part is to understand that today every MRI for 1.5 T, 3 T, or even more is always using supraconductive material. The coils here to do the B0 is placed in a lot of helium, 1,500 liter, and this is a big cost for us. Just to understand how we work, at first you have no current in the coil. You heat some part here, and after you add a power supply outside from the coil here. You start with 0 ampere, and after you grow the current in the coil, after a time you have 1.5 Tesla, for example, and after you cool this again, and after the current is flowing alone without any help from outside. This is very interesting, but this means even if you switch off the power supply of the MRI, you will always have B0. B0 is already present. And this is a big issue for us. If you started to work on an MRI, you know this ferromagnetic stuff is attracted. This video is not from here, but you see what happened here. Even this was, it's an old video, but don't try to do this in your system. You see every ferromagnetic material is attracted to the system, and this could be very dangerous. So the magnetic field is always present, and I can start again. And this is, I think, for me, the main issue for worker and also for us, just to see if something is coming very near to the system, it's dangerous. Just we started some experience here, and this is only a 5-cent coin, and here you see the coin here. You go closer, you see the attraction. Even a small coin is attracted in the system. If you play with this coin, you can just find the magnetic field here. You can find the magnetic field lines. Okay, the guy is working here. You see that you have everywhere a strong attraction here. I will talk more about this in the next course, but just to see this. And the next slide is what is very interesting for us. This was outside. Okay, you see the force is very strong, but inside, I hope you can see the coin here. Inside, you have no force at all. What does this mean? That inside here, you have no attraction again. Only outside, when we have a gradient of magnetic field, you have a strong attraction of the ferromagnetic material, but inside nothing. Okay. So if I just continue my talk, I will explain more about the force and so next course, but just to have the main point here for safety. What we have here, if you have some vital issues, for example, here you have this bed completely attracted by the system here. This is an emergency case. You have to push the quench button. Again, what does this system do here? The quench button here is stopping the magnetic field very fastly. So this, in a few minutes, perhaps less, you have switched B0 from 1.5 to 0. So you can remove all these parts, all the ferromagnetic parts close to the body here. But again, this is like when you're cooking at home, you put some cold water in some boiling system, it's dangerous. So if it's not an emergency case, call the company, the MR company, and they will do what I just showed before. We will start again with 500 ampere and go down until 0, just to go back to 0. And this is less dangerous for the system. So this is a big important stuff for you. If you have your MRI, you have to know where the quench button is, and you have to know when you can use it. What happened again? The idea is we stop the supraconductive system here. If you hit something, the helium will go outside the building here and through this tube here. And after a time, you have no helium liquid, so you have again a resistive material. And after you hit again, and everything goes away in a few seconds, minutes. So the idea just this is when you push the button for the quench button, but sometimes due to some default or stress in the magnet, you can also have an accidental quench, and everything goes away in a few minutes again. The problem is that helium is very expensive, and if you start again this system, you have to put again 1,500 liter helium, and this is expensive. So the idea for you, you have to understand that helium is always here. The magnetic field is always here. So you have to know that the system is a supraconductive system, and you have to know how to stop this. Just for B0, we have a lot of design of B0, and the beginning it was only this kind of system. You have the solenoid here, and generally you have 60 to 70 centimeter. Some systems are going to 80 centimeter. Sometimes you have open system here, like here. This is for claustrophobic patients or babies and so on. There are some design, but it was the same design as this one, but split in the middle. And this was for surgery. And you see the surgeon in the middle here. The patient is here. And it was like in the surgery room. All the coil were just here for single use. This was very expensive, and GE stopped this system. Today, for interventional system, you have this kind of system or this kind of system. There are other new systems. I will give you some other example in a few seconds where the magnetic field is in another direction. Here you stay in the system. Here you can stand in the system. But again, these systems are generally 0.5 system or 0.7 systems, 0.7 Tesla systems. The new system is, this is very funny. This is 64 millitesla. And the idea here, you can plug this in a normal plug just to have a resistive system, and you can go on in the room in the hospital and just do an MRI, but this is only for the head here. So we have some noise. I don't know. You have to switch off your microphone. But what you have to know also for B0, it's not possible to have a homogeneous magnetic field everywhere. So today, generally on a clinical system, you have only in 40 centimeter, 40 to 50 centimeter, the homogeneous magnetic field. And there you have less than 2.2 ppm. This means that only here you can do MRI. If it's not the case, you can do what I call shimming. You can just try to move a bit this sphere here to the place where you want to do imaging, but you have to think that it's only in a few volume that you can do imaging. For this reason, always you push the patient in the middle of the system where we have the homogeneity in some ppm. So if you are outside, it's not the same resonance frequency, so you have at least no image at all, or some gradient, some bad images. If it's not the case, you do shimming. What is shimming? The idea of shimming is that you can do passive shimming at the installation of a system. For example, here you can add some ferromagnetic bar, just that the magnetic field is more homogeneous. And this is needs a lot of work, because you have to ramp up the magnet to add this bar and start again the system. This is very difficult. Today, this is done in the company, in the factory. But what we will do probably in your life is active shimming. This is done, for example, for functional MRI, for spectroscopy. There, what we do is we have you send a radio frequency pulse. You see the FID here. If the magnetic field is not homogeneous, you have the system go very, very fast down. So the system is not in a good way. You change a bit the magnetic field in some place in the system just to have the longest FID. If you have the longest FID, all the range where you do imaging is perfectly shimmed and you can work. Again, for spectroscopy, functional MRI. B0, you have to understand one critical issue. Here I have done the drawing here. In the middle of the system, you have, for example, here 3 Tesla, but we can calculate easily how the magnetic field is going up or down, sorry, down. And this is called the fringe field. So you see here, this is the system, in the middle 3 Tesla. At the end of the table, you have still 50 Gauss. This is 0.05 Tesla. And outside the Faraday cage, you have more or less close to 5 Gauss. 5 Gauss is the limit for people for coming near the system. If you wear a pacemaker, for example, you have not to go closer to 5 Gauss. So you see here the fringe field here, and what we see, there is a big gradient of magnetic field here. And this is the issue for the safety. So you have for some ferromagnetic material here, you feel nothing, you go closer, and after this go very fast to the system and without, and it's very dangerous. Today, almost every system are what we call active shielded. This means that you have 3 Tesla in the middle, but we add some extra coil here just to reduce the magnetic field rapidly outside the coil, outside the system here, just to have this 5 Gauss line closer to the system. So you can have closer rooms, and it's easy and it's less dangerous for pacemaker patient and so on. So 3 Tesla middle and some active coils here. I just go back here and show you this again. Sorry, it was this one. Yeah, this is the active part here of my coil here. In the middle you have B0, but here it's a magnetic field going in the other side of the main magnetic field. This was for B0. I go back, sorry. So the small problem what we have here is for workers. This is my MRTech here, or even if you are working in a system, here you are well placed in the middle of the magnetic field always, just to push the patient inside the system, and so you are exposed to the magnetic field. So this is an issue. I will talk about this in the next course. Today we try to reduce this, and some fancy idea was here by Crozier, just to have a long table here going from outside to inside, or even your place higher. But the problem here is just to reduce the worker exposition to B0. I will talk about this later, but just that you know this, that there is some issue here. Okay, we have seen attraction. The other small problem is the torque here. This is a paper clip inside the system here. You see, when you go inside the system, you have less ferromagnetic material, but the system tries to move and to go inside in the direction of B0. Again here, start again. This is the paper clip. This was X-ray before, of course, and you see there is there's a torque going to push this system inside the B0. And the idea here is easy. This is like a small magnet, and the torque is due to this force here to try to go through the direction of B0. This is still a problem for pacemaker, for all material that we have in the body. You have to calculate this. I will explain this in the next course, how we do this. But the idea is, if you have a B0, the system wants to move to go inside this direction. Another effect for B0, this is an ECG. An ECG outside the system looks like this, for example. But when you go inside, you have all these waves here, what we call hydrodynamic effects here. This is due to the fact that the blood is loaded. You are inside the magnetic field, and what happened there? The ion, the plus and the ion negative are going far in one part of the aorta, and this adds some extra voltages here for ECG traces or EEG traces here. This is not dangerous. This is well known, but you have a strong artifact here due to the magnetic field. I will talk about this later, but if you start the gradient of magnetic field, you will have a lot of artifacts here, and this is another issue here. So take-home message here for B0. Magnetic field is always present. For every system, only a few resistive systems exist. For example, the small one that I showed before, but if not, magnetic field is always present here. And this is a big issue for hazards. And when you come to the MRI, you have to remove everything here. Just for Celine, this was my time in Switzerland with my Swiss knife and everything. And there you have to remove everything, every ferromagnetic tools, you have to remove it. If not, it's very dangerous. And also your mechanic log will stop and everything. You have to think about this. This is easy. The second take-home message for B0, you have the attraction. This displacement force is very strong, and you need a gradient of magnetic field to have attraction. Inside you have no attraction, but outside where you have a gradient of magnetic field, you have a strong attraction, and everything what is ferromagnetic will fly inside the system. Inside the system here, you have no gradient of magnetic field. B0 is homogeneous, and so you have only the torque. The system wants to go in the direction of B0. What you have to remember too, we have only 40 to 50 centimeters where the signal is homogeneous. We can do MRI here. If not, you have to move the patient in the middle. And the last stuff, what I want to mention here is you have to know where is the quench button here for emergency use only. This was for B0. Perhaps you have questions about B0. I can go through again. Ask now. I can drink some water. No questions? Okay, perfect. So I continue. The next step is B1. I mentioned before, to do MRI, you need to send radio waves and you acquire some radio waves. And you will see this is in the radio frequencies. What we have for 1.5T is 64 megahertz, 128 for 3 Tesla, 300 megahertz for 7 Tesla. Just the first point, but it's very important for us. As you know, we have electromagnetic wave everywhere. MRI, of course, but cell phones, Wi-Fi, Bluetooth, and so on. These are always electromagnetic waves. Light is electromagnetic wave, X-ray, gamma wave, and so on. As you probably remember for school, the energy, what we need, when you go higher in frequency, you have more energy here. And after time, it's ionizing. Here in MRI, we are in the range of your cellular phone, radio set, what you have at home. It's not dangerous. You will see there is small, you have to think about something what is called the SAR. I will come through this later. So we are in the low frequency in the electromagnetic wave. And generally we are in the radio frequency range like we have for the radio set what you have at home. What is very important here? What we have here, you have to understand the difference between transmit coil and receive coil. At first, you need some coil which is transmitting the energy to the body. Today, generally, it's the body coil here who transmit the energy inside the body. I just give a number here. We have a lot of power here available, and this could be dangerous. Just your microwave at home is 1 kilowatt. Here you have 33 kilowatt. So we can do here to send the radio frequency with the body coil and do MRI with the body coil. But there the SNR is not so good, so we will need an additional coil. For example, a head coil, a knee coil, a torso coil, just for the reception of the signal here. And this is interesting, is more interesting. Sometimes you have some transmit-receive coil here, like this here, or for example, for the knee, you have also a transmit-receive coil. But generally, you have only the body coil on your system. On resonance system, you have only the body coil for transmission. And what the information here is you have a lot of power, I just mentioned before, and we will call this B1 plus. This is the transmission of the energy to the body. And the issue here is the heating. I will come this in a few seconds. And in the second part, you have a receive coil, and this is, for example, a receive coil, and you will see that you have several designs. Just what I have done here is just to show you how it is working. You will never see this in your life, but here to do a coil, you need a resonance system, an L and C. So you go to the VNA here, and you have to change here the condensator here, just to have the right resonance frequency. You turn in this stuff here, the condensator, and after you try to have 64 megahertz, for example, here, and then you know that the coil is perfectly tuned. It's tuned to the Larmor frequency here. So I start again the system. Sorry, I go back. Zip. So we have L, C. Sometimes you have some condensator here. This is the resonance system here. You want to go in the middle, you have the resonance frequency here. You turn here the condensator, you change the condensator just to go in the middle here. And after you are happy, you are tuned the coil at the resonance frequency. This is the first step here. The second step is matching. I will go through this in a few slides. But what I will mention here, this is very important. Here we have tuned the coil with an empty box here. What happens here? You are very happy here. You have a nice resonance frequency. Here it's changed from an empty box to a box filled by water. What you see here, the resonance frequency is changing. What is very important here? The load is changing the resonance frequency. So if you have a coil, you have to work with the normal load. I will give you some example just in a few slides. But if the coil is not loaded, you have not the same resonance frequency as if the coil is loaded. Some example here. If we have done this in Switzerland, it was a long time ago. If you want to do some babies here, if you use the body coil here for transmission, the load is not good. So the resonance frequency is not good. So you have to use a smaller system here. This was for head, but here you put the complete baby. For example, for very small babies, we use the knee coil here because the load was more adapted to the system here. And this is very important if you do some experiment. If you do not load the system, you have a lot of power coming back here. The system is not adapted. I don't want to speak about matching, but this is because this is changing with new system. But the idea, if the system is not adapted to the load, the power is going back. It's even if you have at home, you start the microwave without something to cook. This is dangerous because the system will send some power, but it's not perfectly tuned, and the power is coming back because you have no load. So think about this. Always load perfectly the coil, just even if you do some phantom experiment. Today, the system is changing. This is, for example, an animal coil here. What do we see here? Here we have the radio frequency is going in both directions to send the radio frequency, and after the receive coil is taking this energy here. But what we see here is all the signal from a modern coil here, you have an integrated amplifier. So you start to amplify the small MR signal to have higher signal, so you have less problems. And what you see here also, we have more than one element. Some information here. We have two types of coils. One is called the volume coil. For example, the body coil is here volume coiled. It's a bird cage design. Here we see what is inside this system here. This is the coil here to transmit radio frequency inside the body. This is also a volume coil, and we call this coil close to the patient surface coil. For example, here for the pelvis, or here the elbow and so on. Okay, so we have two type of coil. Just some video here, you know this. This was a head coil. You have to put the head coil in the middle of the system after you do the calibration, after you go inside the system here. This is a head coil, but where you can select which element you want to use. This is another example here, just that you see an exam. The patient is placed at first without ferromagnetic material, and you will see the placement of the coil. Here, this is a multi-element coil, a torso coil. And you put this in the patient, and after this, okay, everything is placed. What I mentioned before for B0, you do the landmark here. You place the patient here. You have a marker here to see where you have to place the patient. Today, on a clinical system, you have 16, 32, even more elements. We have not only one coil, you have a lot of coils. And you can have even more here, 128 coils here. And what we are working with colleagues in Vienna, we do some flexible coils. And this is more or less what you can find also for some vendors today. Everything is flexible, and you have several elements that you can put together. What is important for us? The coil here, the coil element has to be perpendicular to B0. If you are parallel to B0, you have no signal. So here you see this multi-coil element here. You have here 8 elements here. Always the coil is perpendicular to the main magnetic field. This is for receive signals. For B0, B1, we have to add also the Faraday cage. Probably you know this. The idea here is the signal coming from our patient is very, very small. So if you turn on the MRI without protection here, you can listen your radio set like at home. So every system need a Faraday cage. This means that the radio wave coming from outside cannot go inside our signal. So you have no signal coming from outside. But also that here, I mentioned before, we have a lot of energy here. If you send 33 kilowatts in the air, we have trouble with the police because it's not allowed it. So you have to stop this with a Faraday cage. A Faraday cage is all the room is covered by copper, and this is the shielding place where you put the MRI. Important, the Faraday cage here does not stop B0. Here, if you have a small Faraday cage on the system here, B0, the magnetic field, the static magnetic field can go can you through this Faraday cage. Faraday cage is only stopping radio waves. So I got some details. I'm sorry for some 2 slides are more complex, but it's important for me. What you have to understand is what we call the wavelengths. Today, with 1.5 Tesla here, the wavelength is 4 meters something. At 3T it's half of this, 2.3 meter. This is in air. But when you go inside the tissue, in the patient, for example, you have to divide this by 20 or something like this. So this means, perhaps you remember this, you have seen this, the waves going inside the body here travels with the radio frequency here, but the distance between this sinus here is the wavelength here. Outside is 4 meters, so an antenna of 4 meters is the ideal, but inside the body, it's only 26 centimeters, for example. Why I explain this is if you have something inside the Faraday, inside the body, which is conductive material, this could act like an antenna. This means that the radio frequency will be focused on this. I will explain this a bit later again. Today, what we have to think also is if you have an electrical system, electromagnetic field, you have always magnetic parts and electric parts. In MRI, what we need is B1, is the magnetic part. This is the coil here, what I mentioned before, the resonance frequency here. But we have always an electric part. The electric part is the losses and the heating. And for us, the main issue for B1 is the heating. You send radio wave to the patient will heat due to this SAR here. Some energy will heat the patient. And of course, this is completely controlled, but you have to understand that the SAR, the specific absorption rate, has to be observed. So the energy what you can send to the patient is given in some ranges. And for example, for a normal mode is 2 watt per kilo maximum. This means that if you are going higher, you heat the patient, and this is not allowed. The SAR is, of course, proportional to the number of RF pulses. To the energy for each RF pulse here, 180 degree is has more energy than a small flip angle. And of course, you have to think about the patient weight. The SAR, the energy heating the patient, is proportional to the conductivity of the patient, the E field here, and the density of the patient. When you are working on a system, I will explain this more in detail for everyone on next course, but here you have always the display. You can watch this, you can monitor this, how many energy I send it to the patient for each sequence. And after, if you go higher than a value, you will have some problem. The system is completely controlled by this norm here, this regulation here. And this here, just I show the table, I give this again next time, but the idea here, if you use the body coil, the maximum power you can send is 4 watt per kilo. So you understand that you have to give the weight of the patient. If not, the system cannot calculate the energy. So here, when you are working in a normal clinical setup with a body coil, it's 2 watt per kilo. It's the same as your cellular phone. It's 2 watt per kilo. If you can go higher in MRI, for example, you can just jump, okay, I have not enough power, I will more power, and you can go in the first level mode, and so you send 4 watt per kilo. I should come back to this 2 watt per kilo. This is the same with your cellular phone. If you have 2 watt per kilo, the maximum increase of temperature is 0.5 degree. This was accepted by the international committee. So if you're working in a normal mode, the maximum heating what you bring to the patient is 0.5 degree. If you are going in the first level mode, you have less than 1 degree. Of course, if you're going higher, this is only accepted if you have a service mode or a special mode on the system. You can go higher, but here you are outside what is allowed by the regulation here. Just this regulation gives also some value for the workers. And you see here the threshold for us is 0.4 watt per kilo. What is the problem here? And this is a big issue for me and for us. In practical, if you have no conductive material, everything is controlled by the system, there is no problem at all. The problem is the system is today calculating also how the heating is going up, and so you have to cool the tunnel. Everything is under control on the system. Again, we have a lot of power. Again, I mentioned this before. The SAR is a calculation; it's not a measurement, and so you have to give the right body weight on the system. The problem is the SAR is going up with B0. Okay, if we have 7 Tesla, you have more issue about SAR than 1.5 T. But the main problem for me is if you have conductor material in the system. Here I will give more example next to us, but here you have, for example, this system here. We have only ink here that is conductive. What you see here, you have burning here. If you have, for example, a neurostimulator and the tip on the neurostimulator, you are burning. And this is a big problem for us. We have a lot of examples, and this is a really important issue for us just to calculate this. If the patient has something inside the body, I will explain this later, this is probably not compatible for MRI. So just some information. I don't know if you have seen this before. Today we are speaking about flip angles. Flip angle is the energy just to go in the transversal magnetization. So how we calculate the flip angle? You start with small energy, you go higher, 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 and after a time you are in the transversal mode, and if you go higher, you decrease the amplitude of the FID here. So you can do this, and the system is doing this. What is my flip angle? How many power I need to do a 90-degree flip angle? After this, you can apply whatever 180 degree or less flip angle. Just what I want to mention here, this is happening, this is depending to the patient. So the system is calculating the flip angle, and after it's using this. And mentioned this before, the 180-degree flip angle is a lot of energy. It's twice the 80-degree pulse energy. So the take-home message for radio frequency is used. All the power is absorbed by the body. It's interesting for us to do MRI, of course, but it's dependent of the electrical conductivity and also the electrical field and the density. I spoke a bit about the SAR. This is a big issue for us. You have to control the power what you send to the patient. The maximum power is 2 watts per kilo or 4 watts per kilo, and this is absorbed, and the increase of temperature is less than 1 degree Celsius in a normal mode. If you go higher, you have some problem. You have also the transmit receive information that I mentioned before. Some coils are transmit receive, for example, the body coil, some surface coil, some volume coil like the head coil or the knee coil, and otherwise you use only a receive coil just to acquire the signal. Heating is an issue for implanted medical devices. Just I give you some information later again. Just drink a bit, but to go to the next step for the gradient of magnetic field, if you have questions. So perfect. Celine is doing no, so we can continue. Gradient of magnetic field. This is here when we do imaging, when we run a sequence, we have to add some gradient of magnetic field. One thing is very important, that the magnetic field is in one direction, the direction of B0. When we call about Z or X, Y, or Z gradient, this means always that we are in the direction of B0, but you have a gradient in the X direction, Y direction, or Z direction here. Okay. So how does it work? First, you have the B0 coil here. You add only 2 extra coil here. One wire here, the current is flowing in this direction. The other one is this direction. So you add plus a magnetic field, minus a magnetic field here. And this gradient coil is inserted to the main system here. This means that when you have a sequence, you can apply in X, Y, Z some magnetic field. Just this was the Z magnetic field here. So you can do some encoding. You have seen this probably in several courses before. In an MRI, so you have X, Y, and Z coils here. The green is the Z magnetic field. Here the Y magnetic field in blue, and the X in red here. All this is the theoretical view, but practically you have a lot of paper giving some information. But one recent paper was from Tom Fu, and here you see the design what the people have here. And today I think this is the biggest added value of a system, how the magnetic field is working, the gradient of magnetic field is done, because it's a big issue. I will explain this again. When you have a magnetic field, what are the performance here? If you have a sequence here, you have to go as fast as possible from 0 to the magnetic field added to B0. So this is the time here. What is the slew rate? This is lost time. So you go from 0 to the plateau here. So the first parameter, you have the intensity of the magnetic field here. Today, we have typically 50 to 80 millitesla per meter. In the space, we add some magnetic field going from 0 or minus something to plus something, and the range here is about 50 to 80 millitesla per meter. Again, you remember we are in the middle of the system. Adding to the B0, we add this magnetic field here. As you know, probably this is, for example, a SSFP sequence. This is going very fast. This is a few milliseconds here. So this means that you have to go as fast as possible to the plateau here. Today, we have the slew rate here to go from 0 to this plateau. This is also a value, a threshold value, what we have to follow is 200 Tesla per meter per second. This means about 500 microsecond, 150 microsecond, just to go from 0 to the plateau. And there you switch 0 ampere to 200 ampere. And this as fast as possible. You cannot do this always. Sometimes you are limited by some what we call the duty cycle, because you need a lot of power to do this. And to do today, every system for this gradient of system are cooled by ice water. You will see on the system always some big tube here. This is water flowing through the system to cool down the gradient. If not, you will heat too much the patient. This is some information about the eddy currents. Just to understand that if you have something moving or if you change the current in some conductive material, this is here a plate, conductive plate. You see it's very difficult to move it close to the system. This is due to the Laplace force. I will give some information next course too. So the guy is doing some sport here. He's trying to move it. And just to show you that it's difficult, I think I have here this here. Okay, the plate is going slowly down here due to what we call the eddy currents. The currents is created inside this plate here, and after you have a force called the Lorentz force, this will go against the gravity force. If you are far away from B0, the system is going very fast down. Okay, I will give you this again. So what I will explain here, if you applied the gradient, unfortunately, we have not really what we want. If you apply this to the coil here, the system will go slowly up and slowly down here. This is not good because we want to have a plateau here. In fact, what we need here, after this drawing here, we add some what you call the eddy current compensation. We applied the red light here to have the shape what we want to have here. Because the system is going slowly up and down, we have to have an overdrive of the gradient. And here also to have the glued trapezoidal form here. And this is done in the system, but you have to know this. This is the first point. What we have also, the second problem what we have, we cannot build some gradient of magnetic field completely linear. Here, this was an exercise, example of what I have done in a few years ago. Here you have only small dots here. These are small water tanks. And you do a first image here. As you see, this is not linear at all. This is due because the gradient of magnetic field is not linear. What does it mean? Does it mean that the trajectory in the K space is wrong? So what we have to learn, how the system is not linear, and after we have apply some correction, this is sometimes called the grad warp. And this, after the operation here, you have again your correct image. This is done in the system, it's transparent for you, but here you have to see that the system is not linear at all. The gradient is also the problem for us due to two things. It's the noise. Again, you have here, you change magnetic field in a loop here. This loop is placed in a magnetic field here, B0. This was the gradient, and this is the B0 here. Here you have the Lorentz force. This means that the system wants to move here. If it's moving, it's like the loudspeaker here. You have a magnetic field here, you have a coil here. It's exactly the same here in an MRI. This is the problem, two things. One is noise. This create a vibration in the system and do the big noise in the system. And also you have also this vibration on medical devices. This is a big issue for us you have to check if the medical device can survive after exposed to the gradient. Of course, if you are working in an MRI, you have to add some earplugs or protection just to the noise of the system. The second problem is peripheral nerve stimulation. What I mentioned, we put here the patient in the middle here, and here you see the non-linearity of the gradient here. Here you have a good linearity in the field of view, but outside you go very fast down here. And there you have a large dB of dt. The switches of the gradient is higher what we mentioned before. This means that you will create some extra voltage in the patient. This is called the peripheral nerve stimulation, and you can have some tremor or bad sensation, magnetophosphene, and so on. This is always because you switch very fastly the gradient of magnetic field. If you have a smaller field of view, you have more gradient and you have more dB of dz inside the field of view, and outside the field of view where you have the legs and so on, and you have stimulation. So again, you have to follow some regulation. Generally, we have no problem. If you are in a normal mode, you are lower to the threshold of stimulation. This means 44 Tesla per second. The drawing here is only to explain that you are very far away from the heart stimulation. Everything is under control, and sometimes if you want to have very small field of view, the system asks you, can I go to the first level mode? This means that you are going closer to the threshold, even to the threshold. And there you can have some stimulation. This is not dangerous for the patient. It stops when the gradient is stopping. So for the gradient, what we have here, remember that we are in the XYZ direction. We have this gradient added to B0. Generally, the amplitude of the gradient is 50 millitesla per meter, sometimes 80 millitesla per meter. I mentioned the slew rate. Remember, 150 microseconds to go up to the maximum gradient. We need always some cooling of the gradient. The gradient is the source of noise in MRI. And I mentioned this in the top of the beginning of my presentation. This is also the generation of the artifact on the ECG trace. The problem is the peripheral nerve stimulation. This is under control if you respect the normal threshold. I have a few slides to continue here. Just some issue here. If you are working in MRI, a lot of people are working in MRI, you as researcher, but patient, radiographer, nurses, fire brigade, whatever here, you have to know more or less what I will mention in the next slide here. So just to start about safety here. Again, I will give you more information in 1 hour next time, but the idea here, in MRI, you bring a lot of extra material here. Patient monitoring system here, respirator, for example, also this fire brigade stuff here, or the wheelchair or whatever. This is placed sometimes close to the magnetic field. Inside the body, some patient can have some passive implants, stent. This is a stent, some clips, some prosthetic hips, for example, here. This is for the femur, and this was the knee, and so on. And also active systems here. The difference between both here, active, you have some material, but also some electronics. And the main issue for us is the active here helps. I will explain this also next time. One part is outside, one part is this side. You have a wire here, or for example, the pacemaker here. You have some generator, and here you have some long wires going to the heart to stimulate here. This is an issue for us. So you have to understand that we have to check this if a patient has something like this, or if you are coming close to MRI with some extra material. Here again, the slide is a bit heavy, but just to understand, we have B0, gradient of magnetic field, radio frequency. On the other side, you have the implant, for example. This implant has some magnetic property. If it's ferromagnetic, this will flow inside the system. So you have to know if the system is ferromagnetic. You have also to understand the mechanical property. If you have some vibration or some system, you have to know will this break down during MRI or not. We have also thermal property. If you go to the radio frequency here, everything will heat. If you have a good conductivity, thermal conductivity, you have less heating. At last but not least, here the electrical property here. This is the main issue to see, does this heat or not? I will give you some information next time. But the take-home message here, every material going inside the system has to be labeled. MR safe, MR conditional, MR unsafe. MR safe, you can use it, no problem. MR conditional, it's only on those some condition. MR unsafe, of course, you cannot use it. Some devices are not labeled. And this is not good because you have to go through the system and you cannot use it. MR conditional is the oft permanent system. So you have some pacemaker, whatever, but there you have MR conditional for some magnetic field, some gradient strength, some dB of dt for the slew rate, RF field, and SAR. For example, for a pacemaker, the system will say, okay, you can only use it at 1.5T, 3T. Don't use a SAR of 2 watt per kilo, but only 0.1 watt per kilo. And after you can use it. So you have to follow this. For each medical device, you have to go to this MR conditional condition and see where you can use it. And this is very important. I will go through this next time and explain how you learn, how you can label all this. So I stop here. You have seen, it's the last course here, and you have holiday very soon. You have seen that MRI has a lot of parameters, TRT, 3D, 2D, 3D, matrices, whatever, and you have a lot of sequences. It's really difficult to understand something, but after a time you can learn. Magnetic field, the main point is always present. You have to know how to quench it if it's a vital issue. The gradient of magnetic field is, we need it, but this is the problem to noise, the noise of the system, peripheral nerve stimulation, eddy current on devices and vibration. Radio frequency is the SAR, the main issue. You have to understand this. Just I give you some information about here, some courses here. I like this when you are doing some pulse sequence. This is the main book here. And discover this book here for the technology. This is a very interesting book to learn more about hardware and so on. It's go in the higher level than my course here. And after for safety, I will again explain. I get a lot of this issue for the next course, but this is a very new book, and this is the Bible for me. It's very clear, and it's the best book for safety issue. I think we should have this in every MR site on our research sites. So I hope I was not too long. I think you have some information about hardware, some limits of the hardware, some safety issues here. But again, we can start and try to answer your questions. Merci beaucoup. Thank you very much. Are you sleeping?
So you can also write the question in the chat if you want.
Also, I have the question here. Is this button here to switch off the MRI? Yes or no? Nobody is listening. This happens in some places. The lady was switching off the light, and now we have to power up the machine here. And after, if you push this here, the cost is about 100,000 kilo, because you have to fill again the magnetic field here. So use this only in emergency cases and learn on your system where the quench button is. This is the next step what you have to do tomorrow when you go back to the system. Questions? No questions? So I have another question. I have a lot of questions, so you cannot go back at home. It's here. This is a patient coming with. This is, in fact, it's a defibrillator here. What can we see here? Where are the main risks here? Can somebody help me? This is an X-ray, of course. You understand this? This is the pacemaker here, or the defibrillator. After you have a long wire here going inside the heart here. Perhaps this system is given as MR compatible, so you can use it. What do you think about this here? Discussion. There are some people who are asking something.
So there was an answer in the chat. I can read it. You can't read it. Is that correct?
Yep.
So Colette wrote that coils of wire are equal to the conduction loops plus the electric interference.
Perfect. I didn't understand exactly what you mentioned, but it was more or less the stuff here. Here, of course, this you have some loops here. This is dangerous for the radio frequency. This will be an antenna, and all the power will go on the wire here, and this will hit here. You mentioned also interference from B0. This is to have a little ferromagnetic material here. So you have the B0 line will change due to this here, and this is not good for images. So you have a hole in the system, a black hole in the system. But what I mentioned here, these are abandoned leads here. If you change the pacemaker here, you bring new leads here, and the old leads you cannot remove it, and this is still in the body, and this is dangerous here. This was compatible to MRI, but not this, and this is dangerous here. Okay, and this is here the story here. Attraction when you go inside, torque, the system will move a bit inside the system, but this is more or less under control. Vibration, you can destroy the system, okay, but here it's the abandoned leads here. They are passive conductive material inside the body, which is not under control. Okay. Petite question. There are two questions. Afficher les discussions. I don't know where the question are. Can you read it?
So there was one comment again on the pacemaker. So she wrote, you need a cardiologist specialist present to turn it on to MR compatible mode, and then after turn it back to normal mode.
That's perfect. Yeah, this I will explain later in the next step because it's a lot of information. In theory, you have a MR conditional pacemaker. You have to go at first to the cardiologist. The pacemaker will be switched in a MR mode, so it's not, the pacemaker is still not waiting a pulse from the patient, but sending some pulses every 60 or 70 pulses per minute. And after, you have no control during the exam. And when he's going out of the system, he has to go again to the cardiologist, see of the threshold and all this stuff. Perfect.
And there was just one participant who thanked for the clear presentation.
Merci. So this is too heavy. Stop. If you have a question, you can also ask here. I have 100 mail per day, so I cannot answer very fastly. But and if not, if you are interested in safety, I will talk 1 hour about safety next time. And the date is the 18th of October, I think. Céline, you will be there too for me? I don't know.
Not yet planned.
Okay. More questions?
So I don't see any questions in the chat.
Was it clear? Yes, no?
For me, absolutely.
Okay. So what do we do now, Céline? We stop?
Yeah, we stop.
Okay.
Okay.
Thank you for listening. It was interesting to explain this again. I was a bit fast sometimes, but I think you have the slides. And you can also go to this book, what I mentioned at the end. You have a lot of information there, but happening to what you are doing inside your thesis or your work, your research work, you have to go to this for physics, for sequence, for hardware, and for safety. Merci beaucoup, and hope that you come back in October.
Thank you.
Okay.
Thank you.
Merci beaucoup. À bientôt. Goodbye.
Bye.